Welcome to the AI Checkpoints. Today, we're diving deep into the absolute cutting edge of artificial intelligence, where models are not just becoming more powerful and versatile, but quite surprisingly more human-like in how they actually understand the world. We're talking about something truly game-changing from Meta AI research, a new visual powerhouse called DINOv3.
That's right. Our mission in this deep dive is to unpack what DINOv3 is, why it represents such a significant leap forward for AI agents that, see, and precisely how it achieves its incredible capabilities. We're going to explore how it handles vast amounts of raw data, tackle some major hurdles in scaling AI, and delivers unparalleled performance across a ton of real-world applications you might not even expect.
Okay, let's unpack this. The core idea behind DINOv3, and honestly, a lot of the most exciting work in cutting-edge AI right now is something called self-supervised learning, or SSL. Now, in plain English, imagine an AI learning about images just by looking at them. It's like,
Right.
like a baby exploring the world, figuring out that a dog has four legs and fur, or that a car has wheels, without someone explicitly sitting there and labeling every single object.
Exactly. It learns by finding what the Meta AI research team calls natural co-occurrences in the pixels themselves, basically, patterns it discovers on its own.
What's truly fascinating here is the stark contrast with traditional supervised learning.
Totally. Supervised methods, the kind we've seen in a lot of groundbreaking AI work over the past few years, require meticulously labeled data. Think about the immense human effort that goes into creating data sets where every cat, every car, every tree is painstakingly outlined and named.
Right, that sounds incredibly expensive.
It is incredibly expensive, time-consuming, and frankly, it limits how much data you can actually use. Self-supervised learning, like what DINOv3 employs, sidesteps this entirely. It learns directly from massive raw image collections, leveraging what is essentially an unlimited supply of training data.
Because no humans need to label it.
Precisely. No human intervention needed for the labels.
So why is this self-supervised approach such a game changer for AI vision models? What's the real so what here?
Well, for starters, it's all about versatility. Models trained with SSL aren't biased towards just one specific task. The researchers behind DINOv3 found that these models produce what they call versatile and robust generalist features.
Generalist features. Okay,
Yeah,
so instead of just teaching an AI to identify a cat, you're teaching it to truly understand images.
you got it. To grasp the underlying visual concepts themselves. It's like building a foundation, a really solid one, that can then support pretty much any kind of visual task.
Interesting.
Exactly. And this versatility leads directly to incredible robustness. These models are far less prone to breaking down or performing poorly when faced with unexpected changes in input data.
Which must be huge for certain fields.
Monumental.
Hmm.
Especially for domains where labeled data is incredibly scarce, but raw observational data is abundant. We're talking about fields like histopathology, analyzing tissue samples, where getting human-labeled data is incredibly difficult, or medical imaging, where privacy and expertise make labeling a bottleneck. Consider remote sensing, looking at satellite images, or even astronomy, analyzing cosmic observations. In these areas, raw images are constantly flowing in, but human-labeled examples are almost impossible to acquire at scale. SSL just unlocks these fields for advanced AI.
And it's not just about what exists now, it's about the future, right? With the constant flood of new web data.
Exactly. The no human intervention aspect of SSL means it's ideal for continuously improving AI models over time. They can just keep learning, adapting, and getting smarter without anyone needing to handhold them.
However, as impressive as that sounds, taking self-supervised learning to the next level wasn't easy. I gather scaling these models presented some truly formidable challenges.
That's absolutely right. The researchers found that while earlier versions like DINOv made incredible strides, attempting to scale these self-supervised models to be arbitrarily large and powerful led to serious hurdles. We're talking about issues like instability, what's known as model collapse, where the model simply stops learning effectively, or its internal representation just sort of breaks down. And features actually degrading as training runs got longer and models got bigger. Imagine trying to build a skyscraper and finding that the higher you go, the weaker the foundation becomes.
Wow, okay, not good.
Not good at all. This was the metaphorical mountain DINOv3 was specifically built to climb. It was designed to overcome these fundamental limitations in scaling self-supervised learning.
So how did they do it? Let's dive into the DINOv3 recipe, because it sounds like a fascinating mix of smart data curation, building truly giant models, and this really clever secret sauce they call gram anchoring. First up, the data. The research team made it clear that simply increasing the quantity of data isn't enough.
Right, you need smart curation. You can't just throw everything at it and expect magic.
Indeed.
DINOv3 starts with an immense pool of 17 billion web images, primarily from public Instagram posts, which had already gone through platform-level moderation to filter out harmful content.
17 billion, wow.
Yeah, huge. But they didn't just dump all that data into the training pipeline. They used a sophisticated two-pronged approach for curation. First, for balanced coverage, they employed a clustering technique, like grouping similar things together, to ensure a diverse representation of visual concepts. This resulted in a massive 1.689 billion image dataset they call LVD 1689M.
Okay, so diversity first. What was the second prong?
Relevance. They used a system that could intelligently pull images specifically relevant to particular downstream tasks, ensuring the model was getting the most useful information for what it might eventually do.
Got it.
And they also added a sprinkle of high-quality public data sets like ImageNet1K, which is a classic benchmark in computer vision.
But here's a subtle but crucial detail I read. Their sampling strategy was key. It wasn't just about the mix itself, but how they fed it to the model.
Exactly right. They found that the best approach was to mix it up during training. About 10% of the training batches were homogeneous, just pure ImageNet1K. And the rest were a heterogeneous mix of everything else from their big curated pool. This best-of-both-worlds approach yielded superior results across benchmarks. It shows how a targeted mix can really outperform sheer volume alone sometimes.
Fascinating. Okay, so that's the smart data. What about the bigger brain part?
Right, moving from data to the model itself, DINOv3 significantly scales up the visual encoder. While earlier models had around, say, 1.1 billion parameters.
Which already sounds huge.
It is, but DINOv3 boasts a colossal 6.7 billion parameters in its VT7B architecture.
Whoa.
Think of parameters as the knowledge points or connections within the AI's brain. More parameters generally mean more capacity to learn complex patterns. They also implemented architectural tweaks, like custom versions of the vision transformer with modern position embeddings. Basically, better ways for the model to understand where things are in an image.
And techniques to avoid what they called positional artifacts. What's that about?
Yeah, those are issues where the model gets confused if an image is suddenly a different size or resolution than what it mostly trained on.
Yeah.
Almost like a photograph getting distorted if you blow it up too much without the right tools.
Ah, okay.
These tweaks improve the model's robustness to different image resolutions, making it more flexible.
And here's something that caught my eye. It makes the development process itself more streamlined. Unlike previous versions, DINOv3 uses constant hyperparameter schedules.
That's right. For 1 million iterations, which simplifies training immensely. It allows for continuous improvement without constantly fiddling with settings. Makes life easier for the researchers.
Okay, but for me, this is where it gets really interesting. The gram anchoring breakthrough. This is the secret sauce you mentioned.
This is truly a critical innovation.
Yeah.
And it tackles a very deep problem they discovered. The team observed this fascinating and frustrating phenomenon. As models got larger and trained longer, while their global image understanding improved they could recognize a whole scene perfectly. The dense features, which are the fine-grained details an AI uses for tasks like segmentation or understanding textures, started to degrade.
Degrade. How so?
Imagine a high-resolution image of a fruit stand. The AI might accurately identify it as a fruit stand. That's the global part. But the individual clusters of grapes, or the specific textures of a dragon fruit, would become blurry or noisy in its internal representation. The visualizations the researchers looked at, which show how different tiny patches within an image relate to each other, would simply get messy. It's like seeing the forest, but losing sight of the individual trees.
That's a perfect analogy. And for a generalist vision model, losing the trees is a huge problem.
Exactly. So how did they solve this losing the trees problem? How do you get the AI to retain those fine details at such massive scale?
Yeah.
It's called gram anchoring, and it's a brilliant solution. This is a new objective, a new goal for the model during training that operates on the gram matrix of an image.
Gram matrix. Okay, what's that in simple terms?
Think of the gram matrix as a detailed fingerprint of an image's texture and spatial arrangement. Not just what's in the image, but how all the tiny patches, the bits and pieces, relate to each other structurally.
Okay, like the internal relationship map.
Precisely. By pushing the student model's gram matrix, the one being trained, to match a gram teacher, which is basically an earlier high-performing version of the same model, frozen in time when its details were sharp.
Oh.
DINOv3 manages to maintain high-quality, clean, dense features without compromising its global understanding.
Wow.
What's even more impressive is that even when applied late in training, it can actually repair degraded features. It essentially gives the AI its eyes for detail back.
That's incredible. Like having an AI optometrist for the AI fixing its vision mid-training.
Huh, something like that. This technique is absolutely key to DINOv3's ability to capture fine-grained spatial details, which was a fundamental roadblock to scaling vision models this large.
Okay, that's wild. So with this intelligent data, this massive brain, and the gram anchoring secret sauce, what can DINOv3 actually do? How does it perform out in the wild?
Well, the primary objective for DINOv3 was to be a universal visual encoder that works off the shelf.
Meaning you can just plug it in and use it.
Pretty much. Use it for almost any visual task without extensive fine-tuning for each one. It was designed for extreme versatility right from the start. For example, it's trained to adapt to various input resolutions, from small images all the way to very high resolutions, like 7168 by 46 pixels.
That's huge resolution.
It is. And the researchers showed it maintains stable and consistent features across all these scales, which is crucial for real-world applications where image sizes vary a lot.
And this is huge for practical applications because, let's face it, not every device or scenario has the power to run a 6.7 billion parameter model directly.
Not at all.
That's where model distillation comes in, right?
Yeah.
You take the big brain's knowledge and kind of condense it.
Precisely. The researchers can distill the knowledge from the massive 7 billion parameter model into smaller, much more efficient versions like compact VIT or COMNEX models.
And does it lose much performance?
Almost none. Their findings demonstrate that a student model with nearly 10 times fewer parameters can perform almost identically to the colossal teacher model on many tasks.
Wow. Okay.
This is critical because it makes powerful AI more accessible for different hardware, for edge devices, for scenarios where computational resources are limited. It's not just about building the biggest brain, but making that intelligence widely usable.
So it's not just about raw size, it's about efficiency and widespread usability.
Got it.
And when it comes to the actual benchmarks, the tests.
Yeah, DINOv3 is setting new standards across virtually all core vision tasks. The research indicates it shows significantly superior performance on dense benchmarks.
Dense meaning.
Meaning tasks that require understanding things at a pixel level, the fine details. It consistently outperforms other self-supervised and even weakly supervised models. We're talking about fundamental tasks like semantic segmentation, which is an AI understanding what every single pixel in an image represents on complex datasets like 80/20K, cityscapes, and VOC.
Okay.
It also excels in monocular depth estimation, where the AI figures out how far away objects are in just a flat 2D image, like giving it 3D intuition from a 2D view.
And what about actual 3D?
It also greatly improves 3D world understanding. Significant gains in estimating 3D correspondences between images, figuring out which points in one picture match points in another picture of the same scene.
Essential for robotics, self-driving cars.
Absolutely. And the researchers even showed it enhances advanced models for tasks like camera pose estimation, figuring out where the camera was, and multi-view depth perception. It gives AI a much better grasp of our three-dimensional world.
Okay, what about finding things? Object detection.
New state-of-the-art results on incredibly complex benchmarks like COCO. And its dense features are even excellent for high-level video classification and object tracking, showing remarkable temporal consistency, understanding how things move and stay the same over time in videos.
This sounds like a true generalist. Does it also play well with text? Can it connect what it sees with language?
Absolutely. DINOv3 can be aligned with text encoders, which dramatically boosts its zero-shot capabilities and multimodal understanding.
Zero shot meaning it can do things it wasn't explicitly trained for.
Exactly. It can better connect what it sees with what it reads, leading to improved performance on dense alignment tasks. You could, for example, ask it to find all the furry objects in the kitchen, and it would have a much better chance of understanding because it's combining visual understanding with textual concepts.
That's powerful.
And what's really compelling is its performance on new frontiers, like geospatial data. DINOv3 proves its universality by excelling on satellite imagery. They pre-trained it on a massive satellite dataset, and it achieves state-of-the-art results in crucial tasks, like estimating canopy height from space.
Wow.
And various land cover and object segmentation tasks on satellite photos, identifying forests, buildings, water from orbit.
That's amazing. It means that a general purpose self-supervised learning model like this can often outperform specialized domain-specific approaches for certain tasks. That's a big deal for efficiency and resource allocation in the real world.
It really is.
So what does this all mean for the bigger picture of AI, and what's the ultimate cost of pushing these frontiers? There's always a cost, right?
Well, yeah, it's also important to acknowledge the resources required. Training models like DINOv3 demand serious computational power. The researchers were transparent about this. Training the core DINOv3 VT7B model alone consumed 47 megawatt hours of power,
27 megawatt hours.
resulting in 18 tons of CO2 equivalent emissions just for that one model training run.
And the whole project.
The total carbon footprint for the entire project is roughly estimated at 2,600 tons of CO2 equivalent.
2,600 tons. To give you a real-world comparison, that's about half of all daily return flights between Paris and New York.
Yeah.
It's a stark reminder of the energy demands of pushing AI frontiers this far, and definitely a crucial consideration as we move forward.
Indeed, it's a major factor. But despite the significant resources, DINOv3 represents a remarkable step forward. This deep dive shows us the immense potential of self-supervised learning. By meticulously tackling challenges in data scaling, model architecture, and particularly that dense feature degradation with gram anchoring, DINOv3 hasn't just set new benchmarks.
Right.
It offers a flexible, robust solution for a wide array of visual tasks, from understanding microscopic cells to vast satellite landscapes. It truly pushes us toward AI that can interpret the visual world in a much more generalized, human-like way.
What DINOv3 really shows us, then, is that we're moving towards an AI that isn't just good at one thing, but can truly understand and interpret the visual world in a much more generalized way, becoming like a universal foundation for AI agents.
Yeah, a foundational visual understanding.
It's an AI that's learning to truly see the forest and all the individual trees within it. Finally, hit like and subscribe if you like the content. See you next time.